Precalc, Chapter 7, Section 3, we're going to split this into two parts. So this is just Part A. So we're going to be looking at what's Gaussian elimination to help us solve systems. And so row echelon form is a stair-step form that with leading coefficients of 1 that allows back substitution to solve. So here's one that's already in row echelon form. So we have a leading coefficient of 1 there, 1y here, and 1z. And as we move down these three different equations, they have less variables. So you have a 3 variable, 2 variable, 1 variable. And so we have z's solved for. We know z is 3, so then we can just back substitute and put 3 in for this z in the second equation, and then solve that so we get y plus 9 equals 6. So then we know y is negative 3. And we can plug in the negative 3 for y and the 3 for z and solve that equation as well. So this is just a bunch of back substitution. So we get x plus 6 plus 15 equals 20, or x plus 21 equals 20. So x is negative 1, and we could write that as your order triple, negative 1, negative 3, 3. And so a row echelon form is this form where you have the coefficients of 1 and then your amount of variables decrease in that stair-step form. Gaussian elimination is just converting systems into row echelon form. And so it's the same thing you've been doing. It's just typically for Gaussian, you keep it in this system, in this setup. When you do this, you can reorder the equations. So like the first equation, you can move to the last equation, and you can also multiply the equation by anything you want to both sides. You could add or subtract the different ones, different equations. So the process of solving is the same. We just keep it in the same format. So some notation is, I would like for this one, I would say I can do 2 times row 1, and then I'll minus row 2. So this is kind of some abbreviation on what I'm going to do. And so my result, if I did that, it's going to be, now I'm going to rewrite this first equation. I'm not changing. It's still going to stay this. I do not want to mess with that because I have that leading coefficient of 1. But if I multiply the first equation by 2, it just is going to change those values, and I would subtract the second equation from that. So 2x minus 2x would be 0x. 2y minus a negative y would be 3y. So you're doing some of this mental math here rather than working it all out. And then you have 2z minus z is z. And then I'm going to have 12 minus 3 or 9. And I can rewrite the third equation here because I've not done anything yet with that. If you want to do more than one of those steps at once, that's okay as well. But the step is always to get a 1 value here, and then I'm going to try to get a 0 for the x here, so I only have a term there. Now my next thing is I'm going to try to get a 0 for this next term, so I want to get rid of this x term. So I'm going to do 3 times row 1 and then minus row 3. So kind of the same thing I just did, but I'm going to get rid of the x in the third equation. So if I did that, I'm going to get 3 there, 3y there, 3z, and then I get 18 here. When I rewrite it, again, I want to keep that same first equation. Even though I'm using a new form of it, I'm only going to write the original form because I want the leading coefficient of 1. My second equation, I'm going to leave it 3y plus z equals 9. I'm not showing the 0x. Now I'm going to subtract. So I have the 3x minus 3x is 0x. 3y minus, there's no y's here, but 3y minus 0y is 3y. And then I have 3z minus a negative z, which is 4z. Then I have 18 minus 0, or 18. The next step would be to get rid of this last y down here. And so since my coefficients are the same already, I'm just going to subtract. So I'm going to do row 2 minus row 3. First equation stays the same. Now when I write my second equation, I'm actually going to divide everything in the second equation by 3 to get a coefficient of 1. So it leaves me with a fraction here, 1/3 z, and then 3. But it gives me that leading coefficient of 1. And then when I subtract 3y minus 3y, I get 0y. 1z minus 4z is negative 3z. And 9 minus 18 is negative 9. So the last step to put it in the final row echelon form is just to get rid of that coefficient of negative 3. So everything else is going to stay the same. So we're going to get z equals 3 when I divide by the negative 3. Now I have this in row echelon form, so now I can back substitute to solve. So I can take this 3 value for z and put it back in for z here. So that's going to be 1, subtract 1 to both sides to get 2 for y. And then I can plug in 2 for y. So that top equation is going to be x plus 2 plus 3 equals 6. So x is 1. So we get our order triple 1, 2, 3. So here's another problem. We're going to go through the same setup. For this one, I would call the second equation, I would make it become equation 1 right away. So you could rewrite that if you want to. And I'm okay with you doing more than one thing, one step at the same time. Just be careful with that. Make sure you still show your work. Okay, so now I need to get rid of the x's here and the x's here. So let's try doing both at the same time. So I'm going to do the 3 times row 1 minus row 2. And then at the same time, I can go through and do 2 times row 1 and minus row 3. So that'll get rid of both the x terms in the second and third equation. If I do that, the first equation is going to stay the same. And now in blue here, I'm going to do the 3r1 minus r2. So that would be like the 3, negative 6, and 9. And so I'm subtracting, so I'm getting 0x, 3y minus a negative 2y. Make sure you're careful because you're subtracting, so I'm going to end up adding my y's here. You get 5y. Negative 6z minus 4z is actually negative 10z. And then 9 minus 1 would be 8. Then in purple, I'm going to do it again, but I'm going to do it with multiplying by 2. So notice how I will still show some work up here so I know what numbers I'm using when I'm subtracting, and do that with the third equation. So 2x minus 2x is 0. 2y minus a negative 3y, so again I'm adding there to get 5y. Negative 4 minus 6 is negative 10z, and then 6 minus 8 is negative 2. So the second and third equation are kind of set up here to just get rid of my y. So I'm going to subtract. So I'm going to do row 2 minus row 3. And if I do that, my first row stays the same. My second one, I could divide it by 5. So I get 8/5 here, but that's okay. And then the last one when I subtract, so I'm going to do 5y minus 5y is 0y. Negative 10z minus the negative 10z is also 0. So now I have 0 on the left-hand side here, and 8 minus negative 2 is 10. So now at this point I'm going to stop because I have an issue with this. I get an equation of 0 equals 10. So we have to use our knowledge from the previous section that if this occurs, that there is no solution. So we get a false statement. Another question, 25 here. So I'm going to leave the first equation because I have a coefficient of 1. I can do 2 times row 1 minus row 2. And at the same time, I can do 3 times row 1 minus row 3. So similar to the last problem we just did. If I go through the work to do that, I get, and then I can already see what's going to happen here with these bottom two equations. They're already opposite, so if we go through the mess of actually adding these two, you're going to get 0 equals 0. They are the same equation, they're just opposites. And so our system we could write would be like x plus 2y minus 7z equals negative 4. You see the fishy?
What kind of weird is the fishy?
You see what the fishy has on it? What does the fishy have on it?
A collar.
A collar? It's not a collar.
It's like a dog collar.
It looks like a dog collar, yeah, but what's on top of him? Let's go back to the full picture.
A fin!
A fin, you're right. It looks like a shark.
Uh-huh.
Kind of silly. So I still need to go through and divide by 3, so I get y minus 5z equals -7. And then this bottom equation, when I've gone through and added these R2 plus R3, I get 0 equals 0. And it means there's infinite solutions, but we're not totally done here. We can actually then write relationships for these infinite solutions, because just because there's infinite solutions, it doesn't mean all solutions. And so we can write relationships showing what are the infinite solutions. To do that, we have this third equation say that z equals some number a. We don't know what it is. It could be an infinite amount of numbers, but if we choose some value for z, then we can use it to plug back in the other two equations to back substitute to then find a relationship. So if z is a, in the second equation then, you get y minus 5a equals -7. So then y equals 5a minus 7. So that's what y would be. And I could plug both a and 5a minus 7 into the first equation. So x plus 2 times y, and y is 5a minus 7, minus 7 times z, which is a, equals -4. And then I can simplify this. So we find x is -3a plus 10. So now we have some relationships. We can actually write the order triple using these relationships. So -3a plus 10, 5a minus 7, and a. So if we choose some value for z, then we can find our x and y. So these relationships will represent the... So non-square system, this is a system where there are less equations than there are variables. So that's what a non-square system is. But non-square systems cannot have unique solutions. So similar to the last one where we kind of had to assign z some number and then write relationships, you'll do the same thing always for non-square. So you'll do it for both, for the systems that give us infinite solutions, and you're going to do it for non-square systems. So pretty much for non-square systems, we're going to solve as much as we can solve, and then we'll make up a value for z, some other variable. And so for this one, I would do 2 times r1 minus r2. So here's our system we get, and then we can finalize as much as we can just by dividing the leading coefficient in the second equation. So we get y, so we're dividing by -5, so plus 3/5 z, it should be a z, it should be a z here, equals, and then 3. So then z equals some number a. So that's the third equation. We don't know what z is, and so we'll assign some a value, then we can back substitute to write our relationships again. So y is going to equal a -3/5 a plus 3, and then x, plug it in the equation here. So then x equals -1/5 a plus 1. So then our last one is z is a. So these are 3 relationships we can write for that non-square system.
Oh, I know what to do.
So graphing 3 variables equations, I want to show you visually what's actually occurring here when you're graphing this. And so when you're solving systems of 3 equations, you have these different possibilities for your solutions. You could have some that are none because the 3 planes never cross. You could have one plane because they could all be on top of each other. You could have none where they intersect, but they all 3 don't intersect at the same spot. So 2 are intersecting together at different spots. You could have one point. You could have a single line. So and then you can have infinite solutions. So there's many different possibilities that could occur if you're given 3 equations. So I want to show you visually what could have happened for that. So we're going to call it good for the night for 7-3. Have a good night. We'll see you tomorrow. You wave bye. Say bye. You say bye, Levi?
Bye.
No? You can look right there and say bye.